So because variance and standard deviation and populations and sample stuff is all very similar, I'll probably just put this in one video. The last way we're going to talk about really trying to represent how things are different. In other words, how each person, each event, each outcome is different from the typical average outcome is through variance and standard deviation. Now, both variance and standard deviation are basically two ways of representing the same basic idea. And it's all about deviation scores. And now a deviation score is really just how is some score or value different from the average value. So if I have these different X scores, a 1, a 2, a 3, a 4, and a 5, if I add those up and take the average, I will get a mean of 3. So if I subtract the mean from each score, I will get what we call a deviation score. And in summation notation, it looks like this. When I add up my sum of deviation scores, I have each deviation score here, and then I'm just going to sum across all of those. And so, right, when I look at 1, that's 2 less than 3, so I get a negative 2. 2 is 1 less than 3, I get a negative 1. 3 is 3, get a 0. And then 4 is 1 above and 5 is 2 above. So these are my deviation scores. Again, a deviation score is just how is someone different above or below or equal to the mean. The thing about deviation scores, though, is that if I add them all up, they always add to 0. Always. I mean, everything above, because the mean's kind of that center point, I'm going to have the same weight above and the same weight below. So if I add them all up, I will get 0. So that doesn't really help us that much. Now, in order to get around that, this guy named Francis Galton decided that if we square it and then take the average of the squared deviations, we could have better information. So if you are angry about this particular concept in stats in general, you can direct your hate mail towards him. He was not that nice of a guy, racist, he was like kind of like a Scrooge. So if we square our deviations and add them up and divide by the number of scores we have, then we have a population variance. So variance gives us the average of the squared deviation scores. So going back to this, right, these are my deviation scores. If I square these, I'm going to get rid of those negative signs. So the steps are: list all your data, not in a frequency table. So if I have 2 5s, I write 5, 5. If I have 3 4s, 4, 4, 4, and so on. I calculate my deviation scores, first by calculating the mean and then subtracting it. Then I square my deviation scores. I add up my squared deviations, and then I divide by the number of observations that I have, if I'm doing this for a population. Now, when we look at sum of squared deviations, we're going to call that sum of squares. So anytime I square my deviations and then add them up like I did here, I'm going to call that the sum of squares. And we're going to use that concept, that idea, throughout the rest of this class. It's very foundational to inferential statistics. And the way that looks, right, is I'm going to get my deviation scores here. Then I'm going to square them. And I'm going to add them all up. For the variance, right, what I want to do is get the average sum of squares. So I'm just going to take this equation and divide it by n, or the number of observations that I have. I can shorten it by just writing sum of squares divided by n. Standard deviation is just taking then the square root of this particular score. And what this gets me then, it returns me kind of back to that original scale of measurement, back to my kind of raw deviation scores. Not exactly, but pretty close. When I'm looking at samples, I'm going to change things up. So this is my population variance. Remember, this is my sum of squares divided by n. Again, this is just taking my deviation scores, how every single person or observation is different from the mean, squaring it, adding it up, and then dividing it by the number of observations. That's my population variance. My sample variance, I'm going to subtract 1 from the number of observations that I had. And we'll get to why we do that in a minute. So if I go back to my original numbers here, right, I have my x scores, calculated my mean. I have my x minus my mean, my deviation scores of -2, -1, 0, 1, and 2. If I add those up, I get 0. But if I squared them and then add them up with this little formula right here, right, then the -2 becomes +4, because multiplying any negative number by itself gives me a positive number. My -1 times -1 equals 1, 0, 0. 1 times 1 is 1, 2 times 2 is 4. I add all those up. Now my sum of squared deviations is 10. Now for a population, I will be dividing that sum of squares by the total number of observations I have, 1, 2, 3, 4, 5. That will give me a population variance of 2. Now, if, like in most cases in the real world, I am actually just looking at sample data, because I'm not looking at the whole population, it is very unlikely that I got the extreme unlikely values that are on the really high or low end. So when we think of our normal distribution, right, we are looking at tons and tons of values right around the average or the mean. And as we go really high and as we go really low, there are fewer and fewer people. And if I'm reaching in at random to that population and pulling people out, it's really unlikely that I'm going to find those people or get them in my sample. So typically, sample variance underestimates what the true population variance is. So I'm going to subtract 1 from my n. So this is little n minus 1. And now my variance, if this were a sample, would be 2.5. Okay. Standard deviation, the formula for that is just the square root of the variance. So if we get rid of the square root sign, right, this is just my formula for variance. This s squared is what variance is. Again, s meaning the sum of the average sum of the squared deviations. I use my Greek letters when I'm talking about a population. So again, these formulas are representing the same idea. In standard deviation, you can think of what is the typical distance that somebody's going to be away from the mean. Because variance and standard deviation are all about how are people different from the mean. So when I look at this, right, when I get my population and my sample variances, population variance was 2, sample variance 2.5. My standard deviations are going to be the square root of those. So standard deviation is going to be the square root of 2, or 1.4. Standard deviation, if it were a sample, is going to be slightly larger because I typically underestimate variability in populations when I'm using sample data. And it's going to be the square root of 2.5, which is 1.58. What this means then is if I drew somebody at random from this population, on the average, they'd be about 1.4 points away from the mean. So in other words, that gives me a way to try to say, what's my typical standard difference or standard deviation from the mean that I'm going to see? And you can think of standard as typical, deviation as difference. When I pull somebody out, how far away from the mean are they likely to be? If it's a population, in this case, it's 1.4 points. If it were a sample, it would be 1.58 points. Now, that doesn't mean there's a whole bunch of people stacked up right there. It just means that sometimes I'm going to be higher, sometimes I'm going to be closer to the mean. But on the average, this is how far away I'm going to be. Now, when we have really large standard deviations, that typically means that there are scores that are really far away from the mean. Small standard deviations always mean that scores are pretty close to the mean. So if I have a mean of 80 and a standard deviation of 10, that means the average distance of all the scores to the mean is about 10. You know, there's a whole bunch that are really close. There are some that are farther away, but on the average, they are about 10 points away. If I'm going to use Excel to do this, I can just type variance. So instead of equals average or equals median, I'm going to just type equals VAR. I'm going to open my parentheses, select my data, close my parentheses. For standard deviation, it's just going to be STDEV. And then I'm going to highlight my data again. And I would practice doing this. You're going to have to do this going forward. You know, if we want to look at it graphically, and this is my normal distribution, right? I have my mean right here. The standard deviation always identifies a certain percentage of that distribution. And if we're going out, and if I would draw an equal line over on this side, that middle group, one standard deviation above and one standard deviation below, represents, well, roughly, we'd say about 68% of that overall distribution. And the more standard deviations I get away from the mean, the farther I am and the fewer items or observations there are going to be there. But we can think of this as, right, I have a whole bunch of people who are really close. I have fewer people, but they get really far away, even off this picture. And as I average them out, this is about where it comes to. Now, one of the things that we're going to talk about briefly is the idea of degrees of freedom. And degrees of freedom is usually represented by n-1. It represents the number of items that are free to vary. So if I have, in this case down here, I have these 6 numbers, right? If I know that the mean is 3, those numbers could be anything. Positive 1 million, negative 1 million, 333 kind of things. If I were to start filling in those, right? If I look at my first number and it's a 2, well, I still have 5 things that could be whatever they are, right? Kind of. As I keep adding them up, right? Once I identify, the mean's going to be 3, and once I identify those first 5 values, that last number's value is already determined because it cannot vary, right? In this case, if I'm looking at 3s, right, the 4 and the 2 average out to 3, the 5 and the 1 average out to 3. So in order for this and its pair to average out to 3, it's got to be a 3. There's nothing else I can do about it. It can't be any other value. It's not free to vary. So once I estimate a mean, or even once I estimate the standard deviation, there are numbers that cannot be anything different when I'm working with concepts like means, averages, and standard deviations. You can think of degrees of freedom as like your options, right? And as you make choices in life, which are similar to these different values that we get, right? Your options going forward change. If you quit your job, in one way your options are limited in terms of how you can spend your money if you don't have another job lined up. If you have a kid, if you go to college, right? Some things, they set you on a path and your options do become somewhat limited. Now, the reason then we need to think about degrees of freedom is because this introduces some kind of bias into some statistics. And when we talk about variance, standard deviation, and later on estimates of how much some data can be explained by other variables, bias represents either a systematic overestimation or a systematic underestimation of what the true value in the population is. So if we have an unbiased statistic, that means it is accurate. When I get a sample and I'm trying to say something about the population, it is what it is. However, if I have a biased statistic and I just, use my same formula like we were doing for standard deviation, right? If I just use this with a sample, what I'm going to do is systematically underestimate what the overall variability in that population is. And this has been studied time and time again. It's a mathematical relationship. There's nothing you can do about it. What we're trying to do then is get rid of bias. And that's why we make some modifications. We subtract degrees of freedom. We have alternative formulae to try to get rid of those mistakes that keep occurring over and over. So these are the fundamental concepts that you'll need going forward, right? And when we think about variability, again, we're trying to represent how people are different. We really have 4 tools: the range, the interquartile range, the variance, and the standard deviation. Of these, variance is important computationally. A lot of our statistics depend on that. Conceptually, there's not a lot of use for it. The range gives you the full range of possibilities. The interquartile range gives you kind of what that middle 50% is going to be like. And the standard deviation gives you this measure of, if I just do something at random, how far from the average experience am I going to be, or the average value. And so these 3, range, interquartile range, and standard deviation, are very valuable conceptually. And they should be used complementary to get a full picture of, when I go into something, how do I explain how things are going to be different? It's not going to be the same for everyone. How do I quantify quickly, easily, so people can understand how different the experiences or outcomes might be?